A smooth sphere P collides with an identical smooth sphere Q which is at rest. The velocity of P before impact makes an angle alpha with the line of centers at impact. Alpha is an acute angle. The velocity of P is deflected through an angle theta by the collision. The coefficient of restitution between the spheres is 1/3. So we want to prove this relationship between angles theta and alpha. So we know from the previous video that the momentum of the spheres in the x direction is conserved. So the x direction is the direction of the line joining the centers of the spheres when they collide. So the positive x-axis is pointing to the right. So we want the momenta of the spheres in the x direction just before the collision. So to do that we need the velocities of the spheres in the x direction just before the collision. So here is the velocity of sphere P before the collision. So we'll give it a name. It's not given a name here. So let's call it U. So there's no mention of the speed of sphere P. So speed doesn't, it seems that the speed doesn't come into this problem. So the relationship between the angles theta and alpha is independent of the speed of sphere Q. So we can make the magnitude of this vector anything we like. Anyway, we want the x component of it, so we project onto the x-axis, and here is the x component. We can see that it's positive, it's pointing to the right. So to get its magnitude, we multiply the length of the hypotenuse, which is the speed, that's u without the arrow, multiplied by the cos of alpha. So now we can write down the momentum of sphere P in the x direction. So we take its mass. Well, what's its mass? Well, we're not given its mass, so we just give its mass a name. Let's call its mass m. So the momentum of sphere P before the collision is its mass times its velocity, and we want its velocity, the component of its velocity in the x direction. Okay, and add on to that the momentum of sphere Q before the collision. Okay, P and Q are identical spheres, so if P has mass m, Q also has mass m. So the momentum of sphere Q is its mass times its velocity in the x direction. Well, that's 0 because we're given that initially Q is at rest. So here's the total momentum of the collision just before the collision, and that's equal to the total momentum just after the collision. So let's suppose that P has velocity v after the collision. Well, let's call it Vp just to distinguish from the velocity of Q. Okay, so let's get the momentum of sphere P in the x direction after the collision. So we multiply the mass of sphere P by its velocity in the x direction. So I'll put in the x here to emphasize that we want its velocity in the x direction. And now get the momentum of sphere Q, its mass is m, and we need its velocity in the x direction. So we're taking the components of the momenta in the x direction. Okay, you get this equation. So this equation is independent of the mass. Doesn't matter what the masses of the spheres are. Now, as a matter of fact, Q's velocity after the collision is entirely in the x direction. That's because the force on Q, well, that's because Q started at rest, and the force on it, of course, is in the x direction. So if it starts at rest and the force is in the x direction, it'll just move horizontally to the right forever. So it's the y component of its velocity is 0 after the collision. So you know, we could leave off that x subscript because VQX is VQ. Okay, but I'll leave it in. Okay, next we consider Newton's law of restitution, and that tells us that the relative velocity of, say, P with respect to Q in the x direction is minus e times the initial relative velocity of P with respect to Q in the x direction. Okay, so we apply our relative velocity formula, but in the x direction for oblique collisions. Okay, so what's the initial velocity of P in the x direction? Well, we know what that is. It's u cos alpha. And then minus the initial velocity of q in the x direction. Well, that's 0. So we get minus a third u cos alpha. Okay, let's combine these two equations. So we've got two equations with two unknowns, vpx and vqx. So we'll be able to get each of these two unknowns in terms of u and alpha. They're the givens in the question. The initial speed, well, it's given in the sense that we have it from the outset. So that's what we want, of course. And the easiest way to do this is simply to add these together. So we get 2 vpx equals 1 minus a third u cos alpha. That's 2/3 u cos alpha. And we just divide both sides by 2. So vpx is 1/3 u cos alpha. Okay, so let's indicate the x component of vp. Notice that it's positive. That means it's pointing to the right. Okay, u is a speed, it's a magnitude. U is positive. Alpha is an acute angle, so the cos of an acute angle is positive. So this thing is positive. Now that's important for the picture actually, because if this thing came out to be negative, then vpx would be pointing to the left, so the final velocity of the sphere would be in this direction. We get this kind of a deflection, but that doesn't happen here. So the deflection looks like what we have in the picture. Okay, so that's what we've established. Now we don't have to go and get vqx. We're not interested in the velocity of q after the collision. We're only interested in vp, this vector here, because we're interested in the angle that vp makes with the horizontal. So I'll call this angle beta. Right, let's see how to find beta. If we can find beta, we can get the relation between alpha and theta. So the next piece of information we use is the fact that the y components of the velocities do not change. So here's the y component of u before the collision, and here's the y component of the velocity after the collision. These are the same, as I explained in the previous video. That's because there's no force on sphere P in the y direction. The force on sphere P is along the line joining the centers, so it's in this direction. So the acceleration of sphere P is in the x direction only. There's no acceleration in the y direction. No acceleration in the y direction means no change of velocity in the y direction. So the velocity in the y direction is constant. So what is the velocity in the y direction before the collision? Well, it's the speed times sine alpha. U sine alpha is the magnitude, and indeed U sine alpha is the vector because it's pointing upwards in the positive direction. So upwards is positive, of course. Well, that's the usual convention, of course. So anyway, and this vector here is also U sine alpha. So now we can look at tan of beta, tan of angle beta, opposite over adjacent. U sine alpha over the adjacent. Well, we found out what this is. It's 1/3 u cos alpha. So we multiply above and below by 3, and we get 3 sine alpha over cos alpha. That's 3 tan alpha. So notice here that beta is an acute angle. It's an angle between 0 and 90 degrees. That's because the x component of vp is positive, it's pointing to the right, and the y component is also positive. The y component of the initial velocity is pointing upwards. So beta is some acute angle, and you can see that beta is just the sum of two angles. It's the sum of this angle here, which is actually alpha. See, this angle is opposite this angle here, so they're the same. So this is alpha, and this angle next to it, of course, is theta, what we're interested in. So beta is just alpha plus theta. So there we have it. We have a relationship between alpha and theta. We just have to get it into this form here, and that just involves a trigonometric identity. So, we just have a compound angle formula for the tan of the sum of two angles. So here it is. So tan of A plus B is tan A plus tan B over 1 minus tan A times tan B, where A is alpha and B is theta. So we just have to do some algebra now just to rearrange this to make tan theta, to get tan of theta in terms of tan alpha. Okay, so shift the tan theta term over to the left hand side and factorize out tan theta and shift this tan alpha to the right hand side. 3 tan alpha minus 1 tan alpha is 2 tan alpha. And we just divide across to get our result. A smooth sphere P of mass 2m collides with a smooth sphere Q of mass m. We're given the velocity of P and Q just before the collision in terms of this parameter u. We are given that the impact causes a loss of kinetic energy, given by this value here, in terms of the parameter u. We're going to get the coefficient of restitution between the spheres. So the first thing we will do is get the velocities of the two spheres immediately after the collision in terms of the parameter u. Okay, as usual, the x-axis lies along the line connecting the centers of the spheres at the moment of collision. We can read off the components of each vector. This is the vector 3ui plus 4uj, so the x component is 3u. By the way, we're assuming here that u is some positive value. Okay, consistent with the positive x direction here. We want 3u to be positive, and we want y component of the vector to be positive as well, so upwards is positive. Now we know that momentum is conserved in the x direction, so let's look at the momentum in the x direction immediately before the collision. Let's start with the momentum of sphere P. Its mass is 2m, so its momentum in the x direction immediately before the collision is 2m times 3u. Momentum is a vector quantity. Since u is a positive number, this will turn out to be positive, and that's what we want. The momentum of sphere P in the x direction is positive just before the collision. We want to add to that the momentum of sphere Q in the x direction. Now its mass is m, so we multiply its mass by its velocity. Its velocity is negative. So this must equal the total momentum of the two spheres after the collision. So let the momentum of sphere P be, the velocity of sphere P be v sub P. So its momentum is its mass, which is 2m times Vp. Now Vp is meant to be its velocity in the x direction immediately after the collision. So you could put a subscript x to emphasize that. Similarly, the momentum of sphere sphere Q is its mass, which is m, times its velocity immediately after the collision. So let's say that we'll write that as Vq sub x, the velocity of sphere Q after the collision in the x direction. So we're not looking at y components here. Well, we know that the y components won't change because there's no force in the y direction. The force is entirely in the x direction. Simplifying, on the left hand side we get 6u minus 4u is 2u. Okay, so we've got an equation with two unknowns. U is the given. We want to get each of these quantities in terms of the given quantity u. So next we apply Newton's law of restitution. So here is the relative velocity of P with respect to Q in the x direction immediately after the collision. We know that that's minus the coefficient of restitution times the initial relative velocity of P with respect to Q in the x direction. So E is what we actually want to find. Okay, so we apply the definition of relative velocity. We have both of these quantities in terms of the given parameter u. So let's fill those in. The initial velocity of P in the x direction, as you can see, is plus 3u. The initial velocity of Q in the x direction is minus 4u. So we end up at minus 7ue. So now we have two equations and two unknowns. We can drop these arrows. These are understood to be vectors. So we can write this equation in under the first equation and simply add both sides because the VQX's disappear, and we can get VPX. Okay, next we need VQX, so I'm taking this top equation, make VQX the subject, so it's 2u minus twice VPX. So here we have 2u minus 4/3 u. That's 2 minus 1 1/3, that's 2/3 u. Then minus 2/3 by minus 7 is plus 17/3. Sorry, plus 14 over 3 ue. We can factorize 2/3 u out of this. So for this term we need to have 7 ue. Now we can write down the velocity of sphere P immediately after the collision. So this is the full velocity vector. I'm showing the x component that we just worked out. And as for the y component, well, we know there's no force in the y direction on sphere P, so the velocity in the y direction does not change. So if the velocity in the y direction is 4u before the collision, it's going to be 4u after the collision. Now I'm showing the direction of VP, pointing to the left more or less, but it's quite possible that VP could be something like this. The x component could have been positive. So I'm showing the x component as a negative vector here. This could be positive or negative. It depends on what E is. E, as we know, is a number between 0 and 1. As a matter of fact, if this thing is negative, as I've shown here on this diagram, it means that 2 minus 7e must be negative, because remember u is some positive parameter, so that's not going to affect the sign of this thing. If 2 minus 7e is negative, well, if we solve this for e, we get e greater than 2/7. So if e is greater than 2/7, vector VP looks like what I've drawn here. If e, however, is less than 2/7, then the x component will be positive, so VP will look something like this. Anyway, that's just an aside. Let's look at the velocity of q. Well, we know that the y or vertical component won't change. It's 3u, it's in the positive y direction, so that's going to be the same for q. And as I said, normally the x component shrinks in magnitude, so let's show 3u here on our diagram. So you can see the x component has shrank in magnitude to this new x component, and we know what that is from the previous part. I need to make a correction here. This should be 7e. Now we know for a fact that this thing is positive. Well, e is a positive number, and we're adding 7 times e onto 1, and u is positive, so clearly this is positive. So we know exactly what, well, we have a rough idea of what direction VQ is in. Okay, the x component will be positive. So here's our vector VQ. So its x component is 2/3 u times 1 plus 7e. We multiply that by unit vector I, which is the unit vector pointing to the right, and add on to it the j component, which is positive. So that's 3u. The next thing we do is use the fact that the loss of kinetic energy is given to us. It's 25 mu squared over 2. The loss of kinetic energy is the initial kinetic energy minus the final kinetic energy. Okay, so this will be some positive quantity, because there's always a loss of kinetic energy. The initial kinetic energy is always greater than the final kinetic energy. So by solving this equation, we can find out what E is. Okay, so I've written down the initial and final velocities. Let's get the initial kinetic energy of the first sphere, sphere P. Well, we have to multiply half times its mass. Its mass is 2m, times its speed squared. So what's its speed? Well, here we have its velocity vector. The magnitude of the velocity vector is the speed. So to get the magnitude, we're just using Pythagoras' theorem. We just square both components and sum them, and then we take the square root. But remember, we're squaring the speed, so we can forget about the square rooting. So we square these and sum them. So that's going to give us 9u squared plus 16u squared. That's the kinetic energy of sphere P, and we want to add on to it the kinetic energy of sphere Q. It's half its mass. The mass of sphere Q is actually m, and its speed squared is got by squaring the components and adding them. So it's 16u squared plus 9u squared. So we do a similar thing, of course, for the final kinetic energy. So here's the final velocity of sphere P. So its final kinetic energy is half its mass, which is 2m, times its speed squared. So we have to square the components and add them. Okay, so that's the final kinetic energy. So here is the loss in kinetic energy. So if we take this expression on top and subtract this expression underneath, notice that the terms involving 16u squared will cancel. Okay, we have a half times 2m times 16u squared minus a half times 2m times 16u squared. And similarly over here, the terms involving 9u squared will be the same in both expressions, so they'll give 0 when we subtract them. Okay, so we know the loss of kinetic energy, and we're left with an equation in E only. Now I multiplied all this by 9. Now very fortunately this monstrosity simplifies down considerably. Notice that the term involving E cancels out. We've a plus 28 here, and over here we have minus 2 by plus 14. We have a minus 28. So the E term disappears. So you know, it's going to simplify. This quadratic is much simpler now. It just has an E squared term. Okay, there's actually two solutions to this quadratic equation, plus or minus 0.484, but since E has to be positive, we obviously disregard minus 0.484 and we just accept the positive result,